Okay, let's look at another probability problem where we're actually going to take the idea of rolling two dice and extending it to other types of problems, just to show you how that technique can be used in other situations. Okay, so in this example it says, suppose we have $60 a week in our budget to eat out. And this isn't necessarily true, but let's say my family has $60. And we always like to eat out at one of 5 restaurants. And this is the cost here. One of them is kind of cheap, $18. My family has 3 people in it. 18. One it costs us 25. One costs us 28. One costs us 37. And then one costs us 52. So now let's say each week we chose randomly to eat out 2 times. So each time we chose from one of these 5 restaurants at random. And what I want to know is, what is the probability, if we did that, what is the probability we're going to stay within our $60 budget? Okay? So anytime I do 2 things kind of like this, okay, I can use that table, like with the 6, like rolling 2 6-sided dice, and we have a 6x6 table. Except you can think of this as like a 5-sided dice. Now I don't think there's any such thing as a 5-sided dice, but you could think of it as a 5-sided dice, and one side has 18 on it, another one is 25, another side has 28, and so on. So these are like on the sides of the dice. Okay. And so basically you would have like 18, 25, 28, 37, and 52. And this would be 18, 25, 28, 37, and 52. And this would be like choice 1 maybe. Choice 1, and up here would be choice 2. This would be like the first time we ate out, we randomly select one of the restaurants. This would be the second time we ate out. So 18 plus 18, if we chose the cheap restaurant both times, that would be $36. And we'd definitely stay within our budget, right? Now I'm going to use a calculator just so I get these right. So 18 plus 25, this would be $43. So 18 plus 28, $46. 18 plus 37, $55. And this would be $70. Okay. So now 25 and 18, that's 43. 25 and 25 is 50. This would be 53. This would be, let's see, 25 plus 37. Oops. 25 plus 37. That'd be 62. And 25 and 52 would be 77. So 28 and 18, that would be 46. 28 and 25 would be 53. 28 and 28 would be 56. 28 and 37 is 28 plus 37 would be 65, and then 28 plus 52 would be 80. Okay, so 37 and 18 is 55. 37 and 25 is, let's see here, 37 plus 25 is 62. And then 37 plus 28 is 65. 37 plus 37 would be 74. And then 37 plus 52 be 89. And then 18 plus 52 would be 70. 25 plus 52 would be 77. This would be, what would that, 60, and another 20 would be 80, and 52 plus 37 would be 83, and then 52 plus 52, oh sorry, I didn't read that right, that's 89, and then 52 plus 52, it's 104. Okay, and so this would be our kind of our sample space, right? So we would have the number of outcomes. This is a 5 by 5 square, so there would be 25 outcomes. And we want to know what is the probability that we're going to be able to afford this meal. So we got to count all the ones that are less than or equal to 60. So there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I think that is it. So the probability that it's within budget, and let me see if I can circle these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Be like 11 out of 25. So 11 divided by 25 is 0.44. So there's a less than a 50% chance that we are going to remain in our budget. So we probably shouldn't randomly select the restaurants, should we? We should probably choose some of the combinations that we can afford. And if we eat at this restaurant, then we're going to have to only eat once a week. So that gives you an example of how this concept, this technique, can be used for other problems that in a sense are very similar, but yet they are have a very different feel than rolling dice, don't they? Okay? So the very last video here that I want to share is a quick video talking about sample spaces and the idea of a higher dimensional sample space, which sounds really kind of complicated and technical, but you'll see that it actually comes into play in real world situations.